Hi, I'm Nikhil and I'm an electronic engineer at PA. I work typically in de-risking novel technologies for our clients and turning them into genuine applications. I'm here today at a Global Innovation and Technology Centre, and I'm going to talk to some of my colleagues about the interesting and exciting work that we do with them. So I'm with my colleague Gemma from our Applied Sciences team, and Gemma and I both work at looking at emerging technologies and how they can be useful for our clients. What's an emerging technology that you've seen that's really exciting?
So recently I've been looking at a lot of novel computing techniques, mostly for solving really big optimization problems. And some of the things that we've looked at include quantum computing, and we've also been looking at other things like digital annealing, which is more taking big GPUs and solving a huge problem on them, and they're kind of purpose built to solve that problem. So a lot of the work that we do is comparing these different computational paradigms and how they could be used in different scenarios. So how easy would it be to put something like that on the edge, or how quickly can one thing solve a problem compared to another? So it's really interesting, and we can apply it across lots of different markets, which is great to work with at PA. But yeah, that's me. What kind of thing have you been working on recently?
Yeah, so I've been looking at low power computing and getting kind of intelligence right at the edge. So one of the things that gives us is it means that we can process sensor data right where it's happening, reduces the amount of data we need to send to the cloud in a typical kind of AI fashion where a lot of the processing is happening at the cloud and it's quite computationally intensive. We can actually reduce the kind of power consumption of AI in total by having it right at the point of information entry. There's lots of different technologies with Edge AI. So what we have here is an NVIDIA chip, which is meant to go at the edge, and it kind of consumes in the power of watts. But you can use it for kind of complex image processing techniques. But increasingly, we're seeing different flavors of AI. So things like spiking neural networks, which is actually based on how the brain computes. And that makes a massive difference in how much power it consumes. So we can get really, really low power edge AI and intelligence in the hands of people running on small batteries.
That's really exciting. I think it's interesting how consumers are now going to have a bit more empowerment over how they use their data.
Hi, I'm with my colleague Ahmed from our Electronic Systems group. Ahmed typically works at developing consumer and medical electronics, prototyping them and bringing them to market. Could you talk to me about one of the products that you've actually developed?
This is an example of a medical product that we've developed. It's for detecting PCR, the medical products for detecting PCR, like COVID-19. This is a power supply. It's a thermal cycling power supply to heat and cool peltiers really, really quickly for heating up enzymes and detecting COVID-19. So this is one of the examples. What you've got over there is an example of our consumer products for detecting the height of the water in a manhole. So when manholes get really, really full, this sends data to the internet and tells it that the manhole is about to flood, and the water companies benefit from devices like these. These are fully waterproof, IP67 rated, and we have our own way of certifying this internally.
How do you get better at designing products?
So at PA, we encourage everyone to repair devices and make sure the devices are easy to repair and all our work is high quality. And what we do is we take each person that has a part that's broken, it gets opened up, and everyone learns what went wrong, so our devices do not fall into the same problems, and we learn from the best practices of the industry.
Thanks, Ahmed. I look forward to joining you at the next repair shop. So now I'm with Joseph, one of our applied physicists. So what have we got on the bench today?
So this is actually a prototype of a plasma antenna. So it's something that we've had our interns working on over the summer. But we're really interested in plasma antennas as an alternative to conventional metallic antennas. There's a bunch of really interesting science going on inside of them, and it opens up some potential new functionality and things that you just can't access with conventional systems. Maybe, do you want to talk through what the setup looks like today?
Yeah, so what we have is our plasma antenna. We have a little coil which is attached to it, and that couples in radio frequency modulations into this plasma glow tube. This transmits some radio waves and it's picked up by this antenna. All of this is fed into these two pieces of instruments. We have a signal generator generating the radio waves, and we have an analyzer looking at them and producing this plot.
But what's different about this is that normally you'd have two metal antennas, but we've got a plasma antenna next to our metal antenna. That plasma antenna has some really novel functionality. So not only is it some gas contained in a cell rather than a metallic rod, but actually it's got a property called the plasma frequency, which is something we're really interested in. Because that is a fundamental property of the plasma, but by changing that, we can change how the antenna behaves to different types of RF.
That could be really useful for applications where we don't want to have any interference between the many different antennas. Also, with the plasma antennas, you can turn it off and reduce your protrusion of your antenna. So could you use that to tune things, maybe in space where you want multiple different antennas?
So instead of having to have lots of different sizes and shapes of antenna, you could have one tube with lots of different paths within it, and you could electronically tune it. Or you could control your plasma frequency to make it transparent to other frequencies. And it opens up a whole array of opportunities for novel antenna functionality. So we asked our interns to go off and build one and find out, because there's a lot of literature talking about building these things, but never exploring the use cases. So it's really exciting having one on the bench, but actually there was a lot of work to get here.
So we brought together our science teams and our electronics teams to come together to do simulation and actually build a prototype on the bench. So I'm here now with my colleague Saba, who works as a systems engineer. So Saba, what does systems engineering involve?
My role mainly focuses on talking with the client. When we get a client, and they always come with a vision, so my job is mainly sitting down with them, figuring out whether that's exactly what they need, because sometimes they have some certain ideas but doesn't really equate to what they actually want to achieve from the system they're trying to make. So my goal is sitting down with them, shaping that down, and delivering the final product that actually meets the needs.
Yeah, it's a really good point about how we work with clients to make sure what they build in the end actually meets the requirements, and often that might mean challenging them at the beginning.
That's true, yeah.
And so a lot of the things and systems that we make with clients are often quite critical. So how do we go about building those systems to make sure that they're resilient?
So we start off with an idea, and then obviously once we have the system, we go with possible use cases. One of the things we used, I used recently in my project, was the web diagram. So the main purpose of this diagram is show the client how the various way the system can be used, what are the breaking point of the system, which doesn't necessarily mean that the system is weak at that point, but it means that point is really crucial to the system. So we need to make sure that it's at all time working. So it helps the client to understand that, and also all the various way the system can be used. And again, just because the system can be used in a certain way, it doesn't mean the client is interested in using it that way. So we figure that one out, we filter that out and focus only on what the system must be doing for the client.
So I'm here now with Venancio from our applied sciences team. So how do we go about de-risking novel ideas?
Just imagine this as a 4-step process, for example. So we go from the left, where we get the long-term vision of somebody, then we get to the ideas, and then it's when, at this point, normally, in a normal process, this is designed, and the design becomes something to be manufactured later, and at the end, once it's manufactured, you get to the actual testing at the end. So just to give you a bit of context, at the beginning, people used to get to the manufacturing, and then it's where they could test, but with simulation, we try to shift this towards the left hand. So we try to bring the testing and part of the VMV into the design phase. So this means we bring the simulation in, we are able to test different ideas, as now testing is part of the design part of it. And by doing this job, we can start to analyze feasibility, understanding the design under different scenarios, doing a bit of stress testing, or even running further optimization, but we just take this away from the testing loop. So this is an overall view of how this simulation, they help us to understand ideas or concepts.
Yeah, and I think simulations is great because you can actually probe deep into the physics of what is going on, look at the driving behaviors, And that helps me learn more about the product that I'm designing. So it's not just a stab in the dark when we try and change things. It gives us a more informed approach to our design, and especially, like you said, where there's failure modes and we need to stress test things, we can understand why it's failing and then either put in operating condition limits on it, or we can look at mitigating those failures to ensure we have a product that can survive a large range of tests.